We are here to do the presentation. Our topic is the insect capture design management of the production efficiency of Venice flytrap. The 21st century is seeing health threats caused by global warming. Many countries are advocating for action on climate change to protect public health. My team noticed that here in Taiwan, more and more cases show that abrupt temperature change produces an effect on people. Therefore, we feel the urge to come up with the idea to tackle the problem. First, we found that in the natural, the plant acquires growing nutrition from photosynthesis. However, the carnivorous plants are special. They gain extra nutrition by catching insects. We found that Venice flytrap conduct their production activity through movement. We suppose that we can use this principle to solve the problem. I would like to briefly our experiment. Based on the results, we found that when insects touch the sensory hair, the cell's target pressure of the inside cell will drop immediately and cause the potential energy of the outside cells to convert into kinetic energy. Then the insect catching movement will be complete quickly. Besides, the amount of the sensory hair and the closing time are in negative correlation. Furthermore, sessile gland is responsible for secreting digestive enzyme and absorbing nutrition. We found that it doesn't absorb glycerin, glucose, and vitamin B, but it does absorb amino acid, glycerin, vitamin E, nitrate ion, and ammonium ion. Thus, we speculated that there are some carrier protein on it. What's more, the nutrition absorption and leaf snapping and secreting digestive enzyme are irrelevant. We divided our experiment into 4 parts. They are observing the structure of Venice flytrap leaves, exploring the principle of how it is designed, the connection between the amount of the sensory hair and the closure of Venice flytrap leaves, and exploring the secretion and absorption of the sessile gland. Before conducting the experiment, we have to have a clear understanding of the Venice flytrap leaves. In this picture, we can see there are many sessile glands, which is responsible for absorbing nutrition and secreting digestive enzyme. We can see the shape of it is resembles cyclic structure. The aging sessile gland will wither and the color will fade. Through the resin embedding, we can see the exterior of the sessile gland is composed of 2 layers of cells, while in the interior of it, there are 4 cells which is connected to the mesophyll. In this picture, this is sensory hair. Sensory hair is a structure which receives stimulus. We can see it is connected to the protrusion part of leaf with partition between. As long as the sensory hair is touched more than twice, the leaves will snap. Since the upper epidermis is thicker than the lower one, so it will cause the wart patch and form the structure which looks like stomach.
We observed and measured the inside and the outside cell area of the Venus flytrap. Then we drip 1 molar sugar liquid on them. After 5 minutes, we measure the cell area again. Meanwhile, calculate the percentage of the plasmolysis in order to estimate the target pressure. We discovered that there is not much difference between the outside cell is open and it is closed, and it is open larger than the inside one. However, the condition of the inside cell is totally different. The inside cell becomes larger when it is open and becomes smaller when it is closed. From the percentage of the plasmolysis, the result is the same. From these 2 data, we can assume that the Venus flytrap increase the target pressure of the inside cell and open the leaves forcefully. By doing so, the outside cell will remain in a higher state of potential energy. When the insect touches the sensory hairs, the target pressure of the inside cell will reduce right away, and the outside cell will convert the potential energy into kinetic energy and accomplish the insect capture movement. This is totally different from the slow snapping of the sensitive plant. We would like to know, will the reduce of the sensory hairs will slow down the closing speed? So we designed this experiment. There are 6 experimental groups. Except the control groups, we pull out the sensory hairs every 30 seconds. The next group has 5 sensory hairs, and so on, until there is no sensory hairs. Then we touch the sensory hairs of these 6 experimental groups, making the leaves snap and record the closing time. We discovered that the fewer the sensory hairs are, the slower the speed becomes.
The experiment which we observed the secretion of the sessile gland has divided into biological and non-biological stimulus. In terms of biological stimulus, we put the termites into the Venus flytrap leaves and make the leaves snap naturally. Well, as for the non-biological stimulus, we use the tweezers to touch the sensory hair and make the leaves snap. However, we find that either way cannot cause the sessile gland to secrete. We assume that the sessile gland will only secrete the digestive juice when keeping touching the sensory hair after the leaf snap. Therefore, we put a straw, which is tied with fishing line, into the Venus flytrap leaves and make the leaf snap. Then we pull the fishing line for 10 seconds every other 5 seconds to stimulate the insect struggle, and continues this act for 3 minutes. Then we redo the experiment above with 5 and 10 minutes long. It turned out that only the 10 minutes experiment has secretion. For this experiment, we know that the secretion and the snapping do not have direct connection. The act of snapping doesn't guarantee secretion, and the secretion has positive correlation in how much time the sensory hair has been continuously touched. Thus, as long as the insect is calm enough, there will be a chance to escape. The experiment about the absorption of the sessile gland. We already used the water-soluble red and blue ink and also the fat-soluble blue ink in our preliminary experiment, but there is no absorption at all. We infer that the sessile gland may only absorb the nutrition. As a result, we use the water-soluble nutrients such as glucose, amino acid, and vitamin B, and fat-soluble nutrients such as glycerin, vitamin E, ammonium water, and potassium nitrate together with red ink to observe the sessile gland's absorption towards different nutrients. It turned out that the glucose and the vitamin B are not being absorbed, while amino acid, glycerin, ammonium water, vitamin E, and potassium nitrate are being absorbed. Thus, we infer that the sessile gland not only has a current protein of amino acid, it also has an ion channel for ammonium ion and nitrate ion to go through, which functions as a passage at the root. Moreover, the nutrient absorption, secretion of digestive juice, and the opening and the closing of the leaves are not related to one another. In the future, we can use the work patch of Venus flytrap leaves to design the intelligent biomimetic clothes. This is the principle of Venus flytrap leaves. In these 2 pictures, we can see the cell wall of the inside cell is thicker than the outside one. So when the leaf snaps, it can form a structure which looks like stomach. If we use this principle to design the product, when the product receives stimulus such as light, temperature, and pressure, it can change into reversible assembly rapidly. Through the transformation, the clothes can not only preserve and dissipate the heat, but also protect the human body. For example, We can use two different materials as the basic unit, and the product is composed of basic units. Then under the alteration of the environment, the product can transform its structure due to the work patch. We hope that we can use this material to design to make the common suit, diving suit, spacesuit, and so on. With this transformation, the product can reach the expected effect. Thank you for your listening.